gases mix really easily, and gases can be reactants, products, just like any other chemical. But since they mix so easily, you never have a pure gas. You always have mixtures. But we know from reactions, it may only be carbon dioxide gas that's reacted or produced. Not all the other gases in the mixture, only carbon dioxide gas. So how do you handle the pressure? How do you handle the volume? How do you handle all of that when only carbon dioxide gas is reacting out of that mixture of gases? And how do you make predictions out of it? So that's pretty much what we're going to handle today. And it's going to be a theoretical idea, something that you really can't measure. But it works, and it gives us the right answers. I won't go into the bends, but I've heard that's extremely painful to come up too quickly. And that's a partial pressure issue there, too. So let's go back and see if we can remember how pressure is created in the first place. Shelby, this is a diagram of pressure. This is supposed to be a piston that can move up and down. What could be added to that picture to make it a little better illustration, probably? Make what go on? Yeah, make those little gas molecules move around, right? So the little pistons bouncing up and down, like in the corner up here. And to me, the problem, though, is first I heat it up. Alyssa, I heat it up. What would happen to that little movable piston if I heat it up? The little piston that's bouncing around up there. Right? If I heat it up, all those little gas molecules inside there should start moving faster. So they're going to start moving faster, hit more often, hit harder. Piston should move up, right? So the pressure exerted on that piston, right, is pretty much, all right. So that's a measure of the pressure. But let's say what I wish I could do with this illustration is change all those black circles to red circles and blue circles, right? Because right now they all look at the same molecule. If I change them all to red circles and blue circles, right, nothing really changes because the little piston can't tell whether a red molecule or a blue molecule is hitting it. It just measures the total pressure. Either the piston goes up or it goes down. Okay? So it's a real theoretical idea, but if you could, and it's not possible to do this, if you could distinguish between when a red molecule hit the piston and when a blue molecule hit the piston, then the red molecules would exert their own pressure, the blue molecules would exert their own pressure, but the total pressure still has to be the same. Right? So you have to add up these individual pressures. And that's all we're really doing is this theoretical idea of partial pressures. So the pressure due just to the blue molecules or just due to the red molecules is coined partial pressure. So in this container, we have just hydrogen gas. Okay, and here's the number of moles of it. And in this container, we have just helium gas, and here's the moles of it. So it's pure helium. So the partial pressure, the pressure due to helium is 7.2. There really isn't any partial pressure because it's the only gas. But they put a little subscript on it anyway. And in the hydrogen container, it's only hydrogen. So its pressure is 2.9. But if you take these two containers, put them together into the same container, what would be the total pressure, Frankie? Right? Because I have this, I'm adding pretty much 0.6 moles of hydrogen, right? You can get all the specifics here, but this is what you're supposed to be focusing on. The pressure solely due to hydrogen is 2.9. The pressure due solely to helium is 7.2. Just pretty much just add them together, right? Pretty much just add them together. 10.1 or something, right? Pretty much just add them together, and you'll get the total pressure of 10.1. So if you had 2 weights and you had 5 weights, well, now you're going to have 7 weights. Right? You have 7 weights because it's just the total pressure is the sum of the partial pressures. Even though that partial pressure idea is theoretical, you can't really measure it. It works. Okay? And the total number of moles in the system would be, just add them up. Add up the hydrogen and add up the helium. Okay. So 2.1 would be the total number of moles. Okay. So these problems that are really more real life, these problems that involve more than one gas, they're called partial pressure problems. So we get some new set of equations. And before we had the ideal gas law, Jesus, which was PV equals nRT. Okay. So this ideal gas law had a P in it. Is that the same thing? Christine, is that the same thing? P here was with ATM or pressure, right? ATM pressure, yeah. How about this P? Is that pressure too? Yeah. They're trying to be consistent here. So P is still pressure, but that T, it's total. That T is total. All right? This is total, not temperature. Okay. And you could say the pressure due to A, the pressure due to B, but we're not supposed to. We're supposed to say the partial pressure of gas A, the partial pressure of gas B. And in the question we just talked about, right, there is no such thing as a gas A or gas B. You could have said partial pressure of hydrogen. Get rid of the B. The partial pressure of helium, right? So the total pressure would be the sum of the partial pressures. Okay? But, I mean, you can't really... A and B is really the best way to do it because it takes care of all questions. If there would have been a third gas, it would look like plus PC. Right. Okay. How about this next equation, Gilbert? What is this equation probably saying? We saw a little n before. It was in the ideal gas law. NT equals NA plus NB. Probably means what? Moles. So the what moles? The total moles has to equal the sum of all the individual moles. Right? So the total moles would be just kind of like what we did over here. Yeah. Whatever's in the system, just add them up. Add up the number of moles of helium. Add up the number of moles of hydrogen. So NT is NA plus NB. Okay. These two equations we're not going to see very often, but there might be one of them in the homework, so we need to talk about it. X is called mole fraction. Mole fraction of gas A. So is it a half? Is it a third? Is it a fifth? Well, what's the fraction of this gas? It's actually gas A. It's the mole fraction. So just divide the moles of that gas by the NT was total moles. So if it's half, well then, right, NA over NT would have to be a half.
So you would put 0.60 moles of hydrogen?
Yeah, yeah.
If they ask for the mole fraction.
Yeah, good. If they ask for the mole fraction of hydrogen, you'd have to have the moles of hydrogen all over the total moles. So it would be 0.6 all over 2.1. Okay. And then if you add up all the mole fractions, you better get 1. It's the last one. Okay. If you add up all the mole fractions, you should get 1. Okay. So here's additional equations, but not given on the quizzes and exams. Okay. There's another way to get partial pressures or total pressure. You have to know where to put the subscripts. Let's say we had this this system, right, where it has helium and hydrogen mixed in there. I want to know the partial pressure of helium. So I could just put a little subscript on here, partial pressure of helium, and I could solve for it. But let's put that helium everywhere then, because you really need to. But some places it makes no sense to make the subscript of helium. Now we're after the partial pressure of helium. So pretend we're after the partial pressure of helium. So we put a little subscript on it. Great. So that one's okay. But does it make sense to put a subscript, Amy, on the volume for helium? So here we have this container. Has hydrogen and helium in it. Is the volume the same for all the gases, or is it specific for helium? Same for all gases. So you don't put a subscript on it. It doesn't matter what the gas is. It always has the same volume. It's in that container. Right? Gases take up all the space in that container. How about the next one? N. We're after the moles of gas, Kimberly. Sorry, we're after the partial pressure of helium. And N is the moles of the gas. In this case, the moles of helium, we're saying. Does it make sense to leave that subscript on there? Yeah, because we want the pressure due solely to helium, so that means you better be talking about just the moles of helium. So leave it there. How about Jerixa, the gas constant, R? Does it make sense to have a subscript on the... No, because it's the same for all gases. Good. The temperature. Oh, Christine, the temperature. Is it the same for all? Pretty much you ask yourself is it the same for all gases in this container? Are they all the same temperature? Yes. Yeah, so don't have it. It doesn't make sense to have that subscript. Okay. So if you're after the partial pressure of helium, you just put subscripts on the P and on the N. That's pretty much how it always works. So if you wrote it a general way, partial pressure of gas A, number of moles of gas A. Okay. But a lot of times they're after the total pressure. So you have PV equals nRT. Okay, and it always starts here. And you're after total pressure. So you have to do this. This is what I'm saying is I don't give you these. All I'm giving you is PV equals nRT. They're asking for total pressure. So you're looking for equations that have total pressure in it. Well, here's one. But I'm saying this is another one, and you have to write it. Where else would you put the total, Victoria? For moles, exactly. You got it. So if you want the total pressure, just put in the total moles. If you want the pressure due to any gas, just put in the moles of that gas. Okay? So that's the trick. And since there's so many variations of it, I'm not giving you all these variations. All I'm giving you is the ideal gas law. Okay. Collecting a gas over water. So let's worry about this later. Once I talk about the question and see how to solve it, and then we'll identify the complications. So let's pretend there's not one right now. So if 35 mils of oxygen gas is collected over water at 30 degrees Celsius and 756 millimeters of mercury, how many grams of potassium chlorate reacted? So what does this system look like? So here's my potassium chlorate, and I'm going to heat it. So I don't know, draw some fire down here, right? Whatever fire looks like. So I'm going to heat it. And then the oxygen, right, that oxygen is going to bubble up. The oxygen's going to get formed, and it's just going to bubble up, end up in here. That's where the oxygen gas is going to be. And it'd be nice if they had a little more detail here on this test tube that's inverted over the water. Right? This is a whole bunch of water in here. Right? There needs to be marks. That's how they know that the volume of oxygen is what did they say? 35 mils. So there's got to be some markings on here, right? Oh, 35 mils, right? Let's read the little meniscus. Okay. So we know the volume of oxygen. We know the temperature of oxygen. We know the pressure, right? They want to know how many grams of KClO3 reacted. So again, get used to this idea. If I give you a reaction, if the problem gives you a reaction, it's mole bridge. all they have to do is give you any one of those compounds, and you can solve for what they're asking for. They're asking for grams of KClO3. Well, we're going to figure out which one, and then use the mole bridge to convert it into grams of KClO3. We can use the ideal gas law and get moles of what? What gas? O2, because we know the volume of O2, we know the temperature of O2, right? We know the pressure of O2, right? So this is, all right, we'll pretty much moles of oxygen, and we'll end up converting it to grams of KCl3. So really, this is where I'm at. Is I would call this maybe step 1. PV equals nRT, right? Okay, so we're after moles of oxygen. So I put a little O2 on here. That means I better put a little O2 where? On pressure. Okay. So it seems like we're okay, right? Things are in the wrong units, but the pressure you could put in for oxygen could be, do you see it? Kimberly, you see it? What pressure would you put in for oxygen? 756. Now they're in the wrong units. I'm just identifying it. And then the volume for that oxygen, Gilbert, you put in 35 mils. Again, wrong units, but I'm just identifying stuff. And then we're going to find this one. And R, Monica, remember I gave you that one, right? 0.0821 or something. The temperature, did they give us the temperature? They better have. 30 degrees Celsius. Again, everything's in the wrong units. Okay? So I see that as step 1. Get the moles of oxygen. Step 2 then, right? Convert, right? The moles of oxygen to grams of KClO3. So we'll have to use the mole bridge and then molar mass of KClO3. So do you see the big picture, Shelby? Okay. Now I'm saying there's a complication. So complication to me isn't a conversion or something like that. So, because all of these guys are in the wrong units pretty much. So we got to convert them. That's not what's wrong. What I'm saying is one of these numbers that we identified is wrong. One is off. Either the pressure, the volume, and R or T. Well, R can't be off, so don't worry about R. R should be fine. Temperature, it's just a thermometer. I mean, you just read the room temperature of the room. You really can't, that can't be off either. Well, the moles is what we're after. The volume, well, I mean, you got to be somewhat careful, right? Read the little graduation marks on the test tube. If you're careful, that's not off either. The problem is the pressure. We're saying the pressure due to O2 is 756. That would be true if oxygen was the only gas present. Is it? What other gas is present in here? It's really oxygen gas plus what gas? What gas are you? You can't stop this from happening. A hint is the table. A hint is this table. But you're collecting it over water. Can you stop water from turning from a liquid to a gas? You can't. I mean, you can cap it. Like Amy's got the bottle capped. So the rate and that level of water in that bottle isn't changing over time. So I mean, you can come back tomorrow. It's going to be the same level. So that means the rate of it going into the vapor phase and the rate of it condensing is the same. But if she left the cap off, right, it's just going to keep evaporating. It's never going to reach equilibrium. It's just going to keep evaporating on you. So you can't stop liquid water from going into the gaseous phase. We have water vapor. We have oxygen gas and water gas. Well, but we want just the pressure due to oxygen. We don't want the total pressure. The total pressure, this is total pressure. That's PT. That's the complication. We plugged in the wrong pressure. How do you get the right pressure? Subtract. Good job. Okay, Jesus, let's see if you see the whole number subtract. PT, well, you could write it first. PA plus PB. Okay, fine. PT is PO2 plus P what, everybody? H2O we identified. Okay, my total pressure we know. What number do I subtract to get PO2? 31.8. Good. So in all these collecting gas over water problems, they are going to give you pH2O. They have to. So all you do is you look up the temperature and read across 31.8. And it's nice, convenient units, millimeters of mercury. So my total pressure was 756 millimeters of mercury. That has to equal my partial pressure of oxygen and 31.8 millimeters of mercury. So solve for the correct pressure of oxygen to use, then go do step 1 and step 2 and see how many grams of potassium chlorate were actually consumed. Okay? Try it. Did I lose somebody? Just ask. So this is actually what we're going to do in lab next week. Yeah, it has to be an ATM. Oh, if you want to solve for n, leave n where it is. Bring RT over. in my first step, I got about 1.3 times 10 to the negative 3 for the moles of oxygen. I guess it depends on how many, on your rounding, but you should be somewhere around there. Okay. Once I use the correct pressure, and then you need to do the last step. Convert that to grams of potassium chlorate. I'm not sure where you're at. All right. So the first step would be use mole bridge, and then molar mass of potassium chlorate. See what I'm doing, Melissa? You guys getting it back here? What'd you get for a molar mass of KClO3? Are you doing that now? Well, yeah, it depends on the mole bridge. 2 to 3. Okay, Amy, I'm lazy. What's the molar mass of KClO3? Did you get that? 122.6? Anybody else get 122.6? Somewhere around 120. Right? Yeah, Alyssa says she did. Mole bridge, potassium chlorate and oxygen. I have 2 potassium chlorates for every 3 moles of oxygen. 3 moles of oxygen, 2 moles potassium chlorate. Okay, top multiply, bottom divide. So that's 2. About 0.11 or so. Depends on your rounding, I guess. Okay. Okay, so this is your toughest question that you're going to see in the homework by far. It has pretty much everything. The rest of the homework is just going to be parts, each different parts of this. This is just putting it all together. So the complication is whenever you're collecting a gas over water, and they're pretty much going to say it. They're going to say, we're collecting oxygen over water. We're collecting whatever over water. Then expect to see a table. Right? Or they have to tell you the pressure due to water. And they'll call it the vapor pressure of water, or they'll call it the partial pressure of water. But that pH2O is in that table. So whatever pressure they give you when you're collecting a gas over water, it's off. You have to subtract what Jesus said. You got to subtract pH2O. Subtract it out of there. Okay? And then you get your moles of what you're after. Last step, mole bridge. Okay? So let's see if we can, in your notes, I don't want you to work these out. I think it's best, let's just set them up. Because the plug and chug part, just leave for later. Let's set these up. This first one, EX1. Shelby, we're supposed to calculate the total pressure in atmospheres of a mixture of 0.02 moles of helium and 0.01 moles of hydrogen in a 5-liter flask at 10 degrees Celsius. Now, quiz question, you've got all these equations up there. My strong suggestion is to pick one, right? Because that guides all your effort and all your work. What equation would you pick? P with the subscript T. Okay, this one isn't given though. Do you realize this? Up on the top of the quiz is just written this way. But up on top of the quiz is this one. I'm not saying she's right or wrong. I'm just trying to complicate your life here. Right? Because if I were you, I'd be looking at the top of the quiz. Oh, there's PT. And I'd be writing this one. It's not wrong. It's just going to be more work than what Shelby said. It's not wrong. You have to calculate the partial pressure of gas A, partial pressure of gas B. No big deal. You can calculate helium. Find the partial pressure of helium, right? So fine, PV equals nRT, partial pressure of helium, number of moles of helium. You can find the partial pressure of helium. Just plug in the volume, and they gave it to you, 5 liters. Plug in the number of moles of helium, 0.02. Gas constant, the temperature in Kelvin, and you'll get it. No big deal. And put it in. Do the same for, what's the other? Hydrogen. Right? So you have to do it twice. And then you can get it. It works. There's nothing wrong with it. But Kimberly, why is this one easier? It's less work. Because all you have to do is what, Kimberly? Add up the moles. You see that? Frankie, you see that? Just add up the moles. Because N total would be 0.03. So it's still 2 steps, but the 2 steps are a lot easier. Okay? How about this one? I changed the reaction from your notes. I changed the reaction. What volume of CO2 gas at 21 degrees Celsius and 781 millimeters of mercury could be absorbed by 327 grams copper 2 hydroxide? Frankie, what? You have this big list of equations. What equation could you pick to guide your efforts here? We need to find volume. Good. So pick an equation with volume in it. PV equals nRT. Every single time. Why did he not pick the one with, this has volume in it. But don't use that one. Why? Yeah, there's only one given pressure, one given temperature, one volume. All right, so no, this one doesn't make any sense. Okay. So we're after volume. Okay. Is this one of those weird partial pressure questions where, oh, 781 millimeters of mercury, I got to subtract out the pressure due to water? Is it one of those? No. Don't make your life overly complicated. Only worry about it if it says, oh, collecting a gas over water. So we're after volume. That means we have to know what P is. Do we know what P is? Amy, do you know what P is? you know what the pressure is? Well, it's in the wrong units, but it's just going to be 781. Here's our P. We got that. Good. The volume we're after. We're going to find it. How about the gas constant, Monica? That R. You had to look it up, right? It's that 0.0821 number. Right? Right? We know what it is, 0.0821. The temperature, they tell us that? Jesus, they tell us that one? Yeah, there it is. Whoop. The only one we're missing is N. We need it. The 327 Gs of copper 2 hydroxide, and then find the moles of CO2. I can't stress it enough. Try to get used to it. When you see a chemical equation, don't let it bother you. There's 3 of them up there. If they give you the amount of any one of those 3, you know the amount of all of them. Because it's mole bridge. You just convert. And in this case, they gave us the amount of the copper 2 hydroxide. Fine. Doesn't matter whether they give us moles or grams of it. They told us the amount. So we'll convert this. Convert to moles of this. Okay? I think this would be a good one to try. Let's see if we can wrap up today on this one. Okay. So we're going to use PV equals nRT like Frankie said, but first you got to find moles. You got to find the moles of the gas. And then we'll plug everything in, find volume. If I lost you, just let me know. What's the molar mass of copper 2 hydroxide? No, we stop at moles of CO2 because that little n has to be moles.
It's
98? Thanks. Anybody get an answer? 1.37. I got 156. Did you?
6.7. Yeah.
So somewhere around 156, 157.
Yeah.
Okay, good. That's got to be right. Yeah, because that's what it comes out in liters, because ours in liters
Liters
of CO2. Yeah. Yeah, they said what, but they don't care with the units, so just stick with what ours came out in. Alrighty, so come by and I'll be glad to work some of these out with you.